Okay, so now we want to look at some applications, some Ampere law applications. So let's also look at this in parallel to electrostatic. So let's recall first Gauss law in electrostatic. So the Gauss law was the total flux of the field in a closed surface is determined by total charge enclosed divided by permittivity of the free space. We also have a differential form, which is the divergence of the electric field equal to the volume charge density divided by epsilon zero. So actually we use this, we find this integral form is more useful for us to calculate the electric field. So how do we do this? We need to find a Gaussian surface. On the surface, the electric field magnitude is the same everywhere, so we put it out of the integral sign. So let's recall some two examples. The first one is sphere charge. So we have a uniformly charged sphere. Its radius is r, total charge is q. So how do we find, what is the electrical field at any point outside of the sphere? So the first step is, the most important step is to find the Gaussian surface. So where is the Gaussian surface? The Gaussian surface should be parallel to the surface of the uniformly charged material. So Gaussian surface should be parallel to, the charge. So because this is uniformly charged, then the closed surface that surrounds it would all have the electric field that diverge out, straight out of the surface. So this is the Gaussian surface. Okay, so if we define this radius as r can be any value, so any point outside the sphere. So we have on the left hand side, we have E, and then the total area of the sphere, we have 4 pi r squared. And then on the right hand side, the total charge is just Q, and then divided by epsilon zero. So in summary, here we have E equals 1 over 4 pi r squared, and then Q divided by epsilon zero. Another example is plane. So suppose we have an uniformly charged plane. So the surface charge density is sigma. So how did we find the Gaussian surface? So we want surface that parallel to the charge, to the uniformly charged material. So obviously we need a surface above this uniformly charged plane. It should be parallel to the plane, and we also need to close it. So we get another surface below the plane. It's also parallel to the uniformly charged surface, and we close it. But we assume the thickness is infinitesimally small. So in this way, if the meaningful area is the area above the plane. We have A, and then we have another A below the plane for the pure box. So this is a pure box. The thickness is infinitesimally small. So now on the left hand side here, the total area enclosed would be 2A. Do I have space here? 2A, and then E. And then on the right hand side, the total charge enclosed should be A sigma, because we only have one surface, right? And the projection of this pure box on this plane is just A. So A sigma divided by epsilon 0. So in summary, we have E equals to 2 epsilon and then sigma divided by 2 epsilon. The direction is normal, perpendicular to the uniformly charged surface. Okay, so we have Gauss law, and we learned that how to find Gaussian surface. That's the key. So the way is to find the parallel surface, the surface that's parallel to the the uniformly charged material. So now we have Ampere's law. Magnetostatics. So what was Ampere's law? We have the closed line integral on B equals to mu 0 and total current enclosed. We also have a differential form, which is the curl of B equals to mu 0 volume current density J. Okay, so now our objective is to find Amperian loop. So how do we find Amperian loop? So that's related to the direction of B field. So the direction of B field was defined by Beyond-Savart law, where if it's a line charge, we have B equals mu 0 over 4 pi, and then integral I cross separation vector, unit separation vector, and separation distance square, and dl. Let me have a check. This should be all right. Yes. So yeah. So this is B field. So Ampere loop should be along the direction of B field. So B field is always orthogonal to the direction of current. So based on this, we can conclude that the Ampere loop should always be orthogonal to the direction of current flow. Okay, so this is very interesting. So here it's parallel because in Coulomb's law, that defines the direction of E field. It's not cross product, but Ampere's law is a cross product. It's strictly perpendicular to the current flow that give us the magnetic field. So there is perfect symmetry. Okay, let's look at 4 typical and very classic examples of Ampere's law applications. The first one is line current. So we have just steady current here, I. So what is the magnetic field up and down anywhere around this current? So basically, based on right-hand rule, we know magnetic field would go like this. So magnetic field would go like this. So magnetic field is orthogonal to the direction current flow. Amperian loop should be along the direction of magnetic field. So, or Amperian loop is just this. So on the left hand side here, we have B. So if the distance to the circuit, we denote it as S. So we have the whole closed loop length equals to 2 pi S, and this equals to, on the right hand side, we just have mu zero I. Okay. So B equals to mu 0 I divided by 2 pi S. Okay. Second example is a plane current. So, if we have a plane here, so I have the coordinate x, y, and z. So the current would flow towards x direction. So K, the surface current density, let's say equal to a constant, and then multiply x, unit vector x, so towards x direction. So what is the magnetic field? So here let's recall, because we need to get the direction of magnetic field first. So the beyond Xavier law for the surface current density should be expressed as B equals mu 0 over 4 pi, and then surface integral K across unit separation vector, and then separation distance square, and dA. So basically B must be perpendicular to the surface current. So the Ampere loop must be on the YZ plane. Okay, it must be orthogonal to where the direction of current flow. And also it needs to enclose the current. So we should have an Ampere loop on the YZ plane. So it go a little bit up, it go a little bit down, but the height is infinitesimally small. The important thing is L here. And also based on this beyond Xavier law, we know the current is flowing this way. So for any position that's above the plane, we have some, so here, current is flowing this way. So for any point above the plane, we have the magnetic field flowing towards minus y direction. So above the plane, we have magnetic field flowing in this direction. And then for any point below the plane, we have the magnetic field flow, the direction of magnetic field is just a y direction. So now it's all clear. The direction of the B field is clear, and where the Amperian loop is clear. So we can calculate this by Ampere's law. So here on the left hand side, we have B above the plane and B down the plane. So we have 2BL along this loop. The thickness is infinitesimally small. And then on the right hand side, we have mu 0 I enclosed. What is I enclosed? We have the density multiply L. Okay, so so in summary, so we can move 2L to here, so L is cancelled. B equals half of it, and direction is this. So in summary, we have B equals mu 0 over 2, and then K, and then Y direction minus when Z is bigger than 0. So for any point that's above the plane, we have the negative sign here. And then for any point below the plane, we have mu 0 divided by 2 K Y. So this is Z smaller than 0. Okay, we have 2 more examples to look at. I hope this is very clear now. Okay, so the next example we are going to look at another very classic Ampere law application is called solenoid. So suppose we have, like a solenoid, like a tube here, and then we have current flowing in, and then we along the wire, and then we want the wire like this. So parameters, we should have a surface current where so I is the current flowing on the wire, and N is we have N turns per unit length. Okay, now we need to find Amperian loop. So in this shape, we need to invoke cylindrical coordinate, but it's not that difficult. So first of all, let's look at the direction of magnetic field first, which is very easy. So the wire is like this, then the magnetic field should be pointing up, right? So we already know already know the conclusion for the magnetic field should be like there's only magnetic field inside the solenoid. There's nothing outside of solenoid. Let's look at cylindrical coordinate. We have Z direction, and then we have S direction, which is pointing out, and then we have phi direction. Yes. So the current flowing like this, which means the current is flowing along phi direction. It's circling this solenoid, right? So if current is in this direction, then the Ampere loop can only be, so here we have Z direction, and then we have phi direction, we have S. So Ampere loop should only be placed on the ZS plane. So we can place, for example, an Ampere loop here. We know the magnetic field should go up, but here there's no current enclosed. So B equals 0, that's what we expected. So only when we draw an Amperian loop, this loop would enclose circuit, would enclose current. So for this one, if the length is L, yes. So the outside doesn't have magnetic field, inside would have magnetic field. The total current enclosed would be, so let's write it down. So here we have so the Ampere law gives us B dl equals to mu 0 total current enclosed. So for the left hand side, we have BL, no need for direction here, because you know so this is scalar, this is going to be a scalar, we don't need direction here. We determine the direction based on Biot-Savart law, but right hand rule is already sufficient for us to determine the direction for this one here. Okay, BL, so so right hand side, I enclosed would be equal to, here we should equal to mu 0, and then K is here, so NIL. So L is cancelled. So what we have is B equals to mu 0 Ni, and this magnetic field the direction of magnetic field is along the Z direction when it's inside, and then outside we have 0. Okay, one last example, very interesting example. We have toroid, which is also known as donut shape. So imagine we have, you know, like a 3D donut shape here, and then the wires they surround this structure like this. Okay, and in total we have N turns of wire in total, and the current along the wire is I. Okay, so now we need to decide on Amperian loop. So this also is easier to be analyzed based on cylindrical coordinate system. So we have Z, we have S, and then we have phi. So basically, you can see the current flow like this, which means the current flowing on a plane, like if you have a cross section here. So if you have a cross section here, the current just flow like this. So this is ZS plane. So current flow in this plane, ZS plane. So the magnetic field can only go phi direction. It can only go like the circle. So we have a couple of candidates for Amperian loop. So most straightforward one is this one round. So naturally magnetic field should go like this, right? So this is the direction of magnetic field. So if we have another Amperian loop here, there's no current enclosed, so the magnetic field here would be 0. So inside of this hollow donut, we have magnetic field 0. What about outside? That's a very curious thing. The thing is, the current it go up and down, up and down, up and down. So the total current enclosed for this loop is also 0, because all the up current will cancel all the down current. Okay, so only this one would give us value. So for this inside Amperian loop, we have on the left hand side, so if the radius is represented by S, then we have B2 pi S equal to mu 0 total current enclosed, that would be Ni. Okay, So we can summarize B equals to 2 pi s and then mu 0 ni. The direction is phi when it's inside and then nothing outside. Let me check. Okay, yeah, that's no problem. So in summary, the most important thing here is when we calculate electrical field based on Gauss's law, we need to find a Gaussian surface. Where do we find it? The Gaussian surface should be parallel to the surface of the uniformly charged material. And then for Ampere's law in magnetostatics, we are trying to find we're trying to calculate the magnetic field. So our objective is to find Amperean loop. Where do we find Amperean loop? The loop should be along the direction of the magnetic field, and it should be perpendicular to where the current fly, because that's defined by Beyond-Savart law.